All right. Without further ado, this is another cool dude, Justin, and he's got a great presentation. He actually came up to me and said, "Yeah, I want to talk about this and see what we can learn and go forward with." So you're on, Justin. Take it away.
Oh, I'll take your podium for the laptop if you don't mind. All right, folks. Thank you for having me tonight. Let me see if I can get a presentation up on Zoom if it'll let me. Will it let me without the 5-minute delay that we had before? All right. Just a second. Looks like I have to quit and rejoin Zoom because I had my own privacy and security settings configured to not allow it. No, this is just a side effect of me taking cybersecurity seriously. So the masking tape on the camera here probably tells you a little bit about my trust issues with technology. It's true. It is not paranoia. It is not a conspiracy if it's true. Yeah, somebody let me in. Yes, no? Am I allowed? I'm waiting to join. They have to let me back in. There we go. There we go. Yeah, so for the stand up, I did complete my slides at 5:54 today. Today, and that is how I do most things. So today I'm going to be talking about building stations for satellite and Earth Moon Earth work. Those of you that came to Field Day saw an example of me building a station for satellite and Earth Moon Earth work. And that is part of why I point out that my projects are not meant to be traditionally successful. They're meant to be educational, they're meant to be fun, meant to be interesting. They do work eventually. So I'm going to be very clear and upfront with my goal today. I'm going to try and convince you to make a satellite contact. I'm going to try and convince you that you have the equipment already and that this is very easy. And that's true. For your first contact, there are very easy options. You already have everything that you need. The maybe 5 of you in this room that don't have everything you need, you're sitting in a club with at least a dozen people who'd be willing to lend you a radio and an antenna. That's what this community is. I'm going to try to convince you to make that contact because that first satellite contact is as addictive as the first HF contact. That feeling that you get when you're operating for the first time, making a contact, potentially all the way across the world, no intermediate equipment, in this case a satellite. That thrill makes you want to chase the next one and the next one and the next one. And like any good drug dealer, the second hit's not as fun as the first. So you're gonna have to keep going. And you're gonna get hooked on this. And you're going to want to build a better satellite station. You're going to want to make harder contacts. You're going to want to push the envelope a little bit, and maybe you'll join me in building an Earth Moon Earth mega station, and misery loves company. I'd love for you to join me. I promise it's still fun. Before we get to the how of satellite and moon bounce operations, let's talk about the why. We push HF, or we talk about and promote HF as a club, as a hobby, a lot. And HF is magical. And so why would we bother trying to bounce signals off of satellites or reflect signals off the moon? There's a 250 decibel loss across the path to the moon. Makes it absurdly difficult. Why bother? For me, I can answer this question, and maybe you have similar thoughts. I think we should promote activities that are accessible to technicians. I think we should promote activities that don't require going as far down the rabbit hole of studying and testing. I don't like having conversations with folks that are really interested in ham radio, and I say, okay, in order to do the things that I'm showing you, you have to get the second license in the series before you can do that on your own. And for me, I focus on a lot of homebrew, a lot of building my own antennas, building my own transceivers, amplifiers, low noise preamps, things like that. And if you go and research the options that you have available for HF, and coming from a perspective of not having an electrical engineering degree, not having an RF engineering degree, you're going to find a mountain of materials, of articles, schematics, guides, kits, everything you can think of for everything from the antenna to the most advanced base station transceiver that you can think of. And then if you try that search again for VHF or above, you're going to find almost nothing. There's a lot of great antenna building resources, and building antennas is fantastic. But okay, how do I build the low noise amplifier? How do I build my own 2-meter amplifier? I get that the physics is harder, but where'd the guides go? Where'd the schematics go? Where'd anything go? And I'm not going back to college to learn this. And as much as it's true that those things are a little more difficult as you cross the line into VHF, and they get very difficult as you continue going up into the gigahertz ranges, it's not at the level that we can't tinker with it. And one of the advantages of amateur radio compared to nearly every other radio service is we have the right to build our own equipment. We've passed a test that says we at least know how not to interfere with our neighbors on the spectrum, and we're allowed to tinker with it, even unsuccessfully. So I like promoting those activities and like creating more of those resources for folks. My second reason, and those of you that know me well, I like to develop my skills. It doesn't really matter what that skill is or why I'm developing it. I have government licenses for things I'll probably never do again. Um, it's true. I like the process of learning and developing a skill. And building a satellite station, building a moonbound station is going to require you to develop some skills. You might choose to pull out your credit card and solve a lot of the problems that way, and that's fine. That is the magic wand in amateur radio, is the credit card. But even if you do that, you're going to have to do some independent thought. You're going to have to do some research of your own. You are going to have to understand the subject a bit, at least going beyond your first contact or your first couple of contacts. And when you try that first contact, you're going to quickly realize that you have to be quick about this. You need to communicate clearly and concisely in adverse conditions to make any kind of contact. And I have faith that everyone here can do that. But you're going to develop that skill further if you make more than a handful of contacts. And those skills transfer over into emergency preparedness, into running nets, into breaking through a pileup for getting another DX entity in your log. Likewise, on the technical skills, the antennas are going to have tighter tolerances. They're going to be harder to tune. Millimeters are going to matter. And those improvements in your skills and your workmanship is going to transfer over if you try and build something at HF or lower frequencies. But the most important reason for me, and the most important reason that I do essentially anything in this hobby, is because I can. No one's stopping me. I have a license. Exactly. I passed a test. I have a government license. I'm allowed to do this. So let's talk about that first contact. Let's talk about how to accomplish this. Start with an HT. Dual band HT, mobile rig you already have in your car, and decent vertical antenna is really all you actually need to make a satellite contact. Your HT on its rubber ducky is not going to do it, but a mag mount on the roof, 5 watts, that's enough. You don't need directional antennas. You don't need to point anything. You don't need a rotator. We could make a contact in my truck, just parking in a decent place and knowing where the satellite is. The last part's kind of important. So think about where you can operate from. Operating from a vehicle is great because you can move the vehicle. You're going to need line of sight to where the satellite actually is. You're going to need to know when it's going to be there. You're not going to get the advantages that you have being local, where you have a bit of reflection, you have a bit of refraction at 2 meter, less so at 70 centimeter. You need perfect line of sight. Your neighbor's tree cannot be in the way. But these satellites are not in geosynchronous orbit, flying over you. So if you have a brick wall in your way, or you live in the East Bay and you've got a hill to the side, well, you have to wait for a pass that isn't to your east. That's tomorrow. It. I recommend starting with amsat.org. That's the amateur radio satellite group. All of their resources are free except for their magazine, which is a great read. And if you want to give $80 in membership a year to that group, fine. But one of the tools that they have is a pass predictor. This tells you where satellites are going to be relative to you. All you need is your grid square or latitude and longitude. Pick a satellite. Let's start with the ISS. If you want to do this from your phone, Sat Pathfinder on iOS works well. I think it was a couple of bucks. Look for Sat on Android is free, works reasonably well. You don't need to be complicated at this point. There's 1,000 different software solutions that you could be using. Don't bother. We're going to talk about the station that I built for PAARA's Field Day, and one of the things that kicked us in the pants was the software. Don't worry about it yet. The screenshot here is a list of the next 10 passes of the ISS that I pulled this morning for our location for my grid square in San Jose. Looks like a dense table of data, but really all you need to worry about is the azimuth, which is your compass heading to the satellite when you acquire the signal, when it comes up over the horizon. Tells you the azimuth at the midpoint, the elevation. So that gives you an idea of what that curve looks like, and the azimuth when it goes back down. You can see some of these passes. If you look at the maximum elevation, some of them are kind of low, right? 5 degrees, 10 degrees above the horizon. Look for a pass like this, 48 degrees above the horizon. Pretty much all around us, you're not going to see anything below 5 degrees. We've got a hill or something in the way. Wait for a pass where it actually comes above the horizon a little bit. Your vertical antenna has really great radiation pattern for things that are basically out along the horizon relative to you. Anywhere between 20 and 50 degrees or so, it's perfect. It's an even donut all around. If you're like me and you have a vertical antenna on one side of your vehicle, you probably want to point that towards the satellite. The roof of my truck is probably not great for line of sight, but you don't really have to worry about exactly where it is, as long as it's not directly over your head, above around 60 degrees elevation on a vertical antenna, you're into the null at the top of that antenna. But if it's just roughly out from you, be fine. We're going to start with the ISS because this is the easiest satellite contact that you can make. It's transmitting 25 watts. And for space, that might as well be a million. Every other satellite that we as amateurs have the ability to make a 2-directional contact over is in the milliwatts range, right? Some of them are tens of milliwatts. And that's for size and space and weight concerns on launch. But the ISS is massive, and it has regular resupply missions. So 25 watts is probably 0.0001% of its power budget. for that service versus the CubeSat, where the only thing it's running is the transmitter and it only has a few milliwatts to do that. This is big. It's easy to find. You don't actually necessarily need the pass predictor. At the right time of day, you can just see it. And 25 watts, you should be able to pick it up really well. All you have to do is find a pass that's good for your location, set up, turn your squelch all the way down, and listen. As it comes up into range for you, you're going to hear a little change in that static. You're going to start hearing broken transmissions, and then you're going to hear it. And it's just an FM repeater. Listen. When you find a break in conversation, key up, send your call sign, send your grid square. Someone will call you back. That's it. These contacts are incredibly quick. Call sign, grid square, thanks, and have a nice day. That's it. It's an FM repeater. You transmit up, you transmit with a PL tone. The only slight complication is it's going to transmit back to you on a different band. The ISS is 2 meters up, 70 centimeters down, and you can get the frequencies and the specifics from AMSAT for all of the various satellites, and basically everything is going to be in that range. It's going to be 2 meters on one way, 70 centimeters on the other. 2 up, 70 down is common. Some of them are the other direction. That's all you need to worry about. This contact, I promise you everyone here can make. Now, if the good pass for your location is at 2 o'clock in the morning, I recommend waiting a day or two until the pass is at a reasonable time, because everyone that could possibly be answering you, it's also 2 o'clock in the morning, or they're east of us and it's 4 o'clock in the morning. So there is traffic on the satellite at that hour, but don't make your first contact harder than it needs to be. There's a small bonus for the ISS. You might have an astronaut answer you. They do occasionally, scheduled and unscheduled, just decide to operate over their own repeater. We heard this on field day. For us regular hams, you're going to get a hello, and then they're going to be off to the next person because news travels quickly when the astronauts start answering calls. If you have a school group, scouts, something like that, you might be able to get a sked and actually have a bit of a conversation. Don't expect more than a hello as a random ham that popped on the air one day. I'm going to assume you're addicted now. Where do we go from here? There's half a dozen or so operational FM repeater satellites at any moment in time. Some of them have some complication that you have to send a different PL tone to wake them up. Some of them are very low power, but they're all effectively FM repeaters in space. Just happens to be crossband. When you move on from the ISS, you can get a little bit further range. You've got about 1,600 miles on the ISS. And that maximum range occurs when the satellite first comes above our horizon. Because if you are on the edge of the possible range, most of the people in that range are far away from you. If the satellite's directly over your head, your maximum range shrinks to half of the possible range because you are in the middle of the circle. It's not that interesting to make a contact over the satellite with your neighbor. Going to some of the others, they're at slightly higher orbits, and that's really the definitive factor here. The higher they are in orbit, the bigger the cone that they can see, and the more people, the wider range can make a contact over them. None of these satellites have directional antennas or sharp cones or something. A question? I can take questions at the end or now, up to the command and control here.
Yeah.
Doesn't bother me.
Oh, do you have any of the old ones? I remember 60 years ago, they were called Oscar. Are any of those still running?
I forget the call, but there is one ancient satellite still in operation. I believe it's a linear transponder satellite, and it failed for a long time. The battery shorted out, but then at one point the failure turned into an open. So as long as it's in sunlight, it's operational. So it comes up. I believe that's one of the linear transponders, and you get a little bit further with those. If you want to consider an upgrade at this point to get more satellites and get those contacts easier, first thing to consider is your antenna. I recommend looking at turnstile or egg beater style antennas. A lot of folks will recommend directional antennas. They'll recommend arrows. I like arrow antennas. They're great for satellite work, but they're going to add a dimension here that I don't want you to have to deal with as a beginner, and that dimension is polarization. So if you have a directional antenna, you have to point it in azimuth and elevation, but if it's linearly polarized, like regular Yagi, and arrows are just two Yagis perpendicular to each other, one for each band, you're going to have to rotate your wrist to match polarization, and that's just a factor that's going to make it more difficult, and it doesn't really increase your range that much. 8 beaters are more like a vertical antenna, but they have really poor performance down, so the donut doesn't really point to the ground. You don't get a lot of ground effects, and they don't have the null at the top, so you can receive and operate when the satellite's in higher elevations relative to you. But again, that's not that interesting. The 8 beaters are just nice for a little bit of gain. You need a slightly better SWR match on them. You are going to be running 2 antennas though. When you get to those other satellites though, you're going to want to start thinking about Doppler shift correction. On the ISS, I didn't tell you to worry about this. And the reason for that is on FM, we have the FM capture effect. And on a repeater, you have that benefit on both sides. So the satellite is demodulating an FM channel into audio, moving it over, modulating it, and transmitting it again. For FM, you just have to get enough energy through the receiver's filter for it to be demodulated. It doesn't actually matter that you're centered in that receive. So if you're off because of Doppler shift, and you will be if you're not correcting, all that's happened is you've lost a bit of energy, right? Your signal's slightly off center, and so you've lost some of it to the skirts of that filter. But the ISS is transmitting 25 watts. And I'm telling you to at least use an HT at 5 watts. It actually doesn't matter that much if you're a couple of kilohertz off. I'll repeat the question. So the question is, how much power do you lose? I don't know the math. You're only going to be a few kilohertz off from perfect in the worst case scenario for Doppler shift on these bands. At least I think it tops out around 5 kilohertz on the 70 centimeter band. That's not good. You're probably losing 70% of the power at that point, but I'd have to do the math to find out what it is. I can tell you can absolutely make that contact, and it might be that I'm using a cheap HT with a barn door front end, but if you use a good HT, you might actually have more trouble. For a quick refresh, Doppler shift occurs because relative to you, the satellite is approaching very quickly on the first half of its pass. As it gets to the high point in its pass, that speed drops to 0, and then it's moving the other way. And so as it's approaching you, all of the transmissions, both directions, are compressed, and they rise in frequency. And as it's moving away from you, all of the transmissions are stretched, and they lower in frequency. So since the satellite doesn't know where you are, doesn't care about you, and is just leaving its transmitter tuned and its receiver tuned to the same frequency, you get to provide the correction. On the first half of the pass, that means on receive, you have to expect a higher frequency and tune up a little bit. Works out to 1 to 2 kilohertz on 2 meters. But since this is a percentage of frequency, it's roughly triple on 70 centimeters. You'll find most satellite operators for FM just ignore the 2 meter side entirely, and they apply some rough correction on the 70 centimeter side. Your typical mobile rigs and HTs are not going to give you 100 hertz tuning. 1 kilohertz is great, 2.5 is fine. Again, we have the capture effect from with an FM transmission, so we're just trying to get close to the center of the filter. Nothing else really matters. Those large, rough corrections are perfectly fine, but something to remember is on transmit, the adjustment is opposite. So as the satellite is approaching you, whatever you transmit goes up in frequency, and you have to tune down to compensate for that because the satellite isn't providing correction. But on receive, it's transmitting at whatever according to its perspective, that frequency is, and it's coming in higher. So on the first half of the pass, you're tuning receive up and transmit down. And on the second half of the pass, you are tuning receive down and transmit up, which gets fun managing both sides of the radio. I'm going to assume again that you're addicted and enjoying this. You all can tell me the next meeting if I get that wrong. The fun really begins when you get to the linear transponder satellites. You've got another half a dozen to work with. And rather than demodulating the signal that you transmit and cleaning it up, remodulating it, sending it back down as FM on a different frequency, these satellites effectively pick up a band, drop the noise, amplify it, and put it back down on a different frequency. They don't care what the content of that band is. Some of them are operating with bands of 20 kilohertz or so. The best ones are operating with a band of 100 kilohertz. And they don't care what's in it. They just pick it up and they set it back down. You're going to need to stick to SSB and CW for these. FM transmissions are too broad. They take up too much power. And in some cases, the transponders like to mangle FM, but they will do SSB and CW just fine. Your Doppler shift correction in this case is going to be critical on both transmit and receive. Being 100 hertz off on SSB, you're listening to chipmunks or you're listening to Charlie Brown, womp, womp, womp. You need to provide that correction, and you're going to need to change that correction as the satellite passes. And for the sake of whoever you're having a QSO with, you should be doing so on transmit as well, so they don't have to be chasing you up and down the band. CW is a little easier because the tone will shift, but as long as it stays in the filter on your receive end, doesn't matter if it shifts a little bit, you should still be trying to be kind to the person on the other end. And most CW operators who try satellite realize that their receive speeds are a little lower than they had hoped because your ear doesn't really like the sliding around. But it's doable. And the huge advantage here is we can have multiple QSOs on a single satellite at a time. And we don't destroy all possibility of communication when we double with each other. You get the classic SSB pileup. You can pull out call signs or parts of call signs and call them back. Versus on FM, two roughly equal signals, unless somebody is far above the other in power, it's just destroyed. And you'll hear that a lot on the FM satellites. This is why on field day, they only let you have one contact over an FM satellite. It's a zoo. Don't try your first contact on field day. Another advantage that you'll get is longer ranges due to higher orbits. I believe A07 here is actually the satellite that Andy was thinking of is the old, the ancient satellite that came back from the grave. I could be wrong. That's the one? Yeah. Confirming that Oster 7 launched about 50 years ago. So this is a satellite that was not operational for a long time and then failed into a better state, and we get to use it now. But it's in the highest orbit of all of them. You've got about 3,500 miles of diameter on the usable range of that satellite. And if you think about that, that's all of North America, effectively. You can get a worked all states on satellites. You can get 4 different DX entities. I think Alaska counts separately. I believe you might even be able to get some of the islands in the Gulf, purely off of satellites. So you have more like an HF operation. You have pileups and multiple QSOs in a band. You have folks putting CW at the bottom of the range and SSB on the top. It feels a lot like operating CW. You have a lot more opportunities for consistent contacts and quite a bit of range that you can accomplish. There's some upgrades to consider here. Really recommend looking at your Doppler shift correction at this point. There are transceivers on the upper end, things like the IC9700, and there's only a handful that do SSB and CW on these frequencies anyway, that will help you with your Doppler shift correction. They can automatically apply the the same correction that you apply on one side to the other. So if you're tuning receive, they will do the math for the transmit side and apply the correct upgrade. Some of them will even try to handle Doppler shift correction entirely automatically. I find that they're very bad at it. But some of them, like the 9700, will zero beat an SSB signal really well. And on HF, I find that to be an annoying feature. And I'm thinking, why? I don't need you to figure out where the signal is. I can turn the dial myself. But I'd like you all to imagine trying to zero beat that signal while it's moving. The 9700 does really well. There's some HT options. There's some mobile rig options. Most of the, actually, I think all of the HTs and all but one of the mobile rig options are out of production currently, but you can find some really good deals on eBay, on swap meets, QRZ, that sort of thing. If you're running base stations, if you have a bit of coax, you're not in your vehicle, you're not operating pedestrian portable or POTA like I usually do, you'll probably want to consider a low noise amplifier at the antenna. VHF and above, your coax losses start to add up really quickly. And so putting an LNA at the antenna side can actually make a lot of contacts possible. Your hardest thing is going to be hearing that satellite. If it's transmitting milliwatts and it's thousands of miles away from you, it's a little difficult. So put the LNA up at the antenna if you can. The transceivers will often have a good LNA built in, but that doesn't help with coax line losses. If that signal dropped below the noise floor before it got to the radio, nothing else matters.
How much power are you typically using?
This is a case like terrestrial repeaters, where any more power than what the other side is transmitting is pointless, right? So 25 watts for antennas or for satellites is overkill with everything except the ISS. So this is all HT level power. 25, 50 watts on a mobile rig is totally fine, but also completely unnecessary in most cases. You can upgrade your antennas at this point too. Don't upgrade power. Don't worry about it. The gold standard for satellite work is circularly polarized antennas. And the reason for this is the satellite is either circularly polarized itself, in which case it's expecting you to be right-hand circular polarization, or more likely it's some kind of linear polarization. It's often using the same antenna for 2 meter and 70 centimeter. Circular polarization matches to any linear polarization at a 3 dB loss. So if you're linear and you're 90 degrees off, you have a -20 to -30 theoretical match. If you're perfect, you have a 0 dB loss due to polarization mismatch. But if you have a circularly polarized antenna, you will always have a -3 dB loss. And you can make that up elsewhere in the system. That's nothing to worry about. So circular polarization is the gold standard for satellite work. The 8-meter antennas that I recommended, those are circular polarization, assuming that they're tuned properly. You can do this with Yadis, the Yadi UDA antenna. It's common to use cross polarization, which is effectively building 2 identical Yadi UDAs and rotating the second one 90 degrees and shifting it 90 degrees in phase. If you came to field day, this is how those antennas were designed. They were 2 identical perpendicular Yadi UDAs, and the second one was moved forward in space by a quarter wavelength, because I'm not going to bother trying to make a match out of coax. All you have to do is tie them together with a Y, and you have circular polarization. And whether it's left hand or right hand just depends on the polarity of that at that Y. Those are really common. There's lots of different options for them. If you're going to have any significant amount of gain, you're going to have to start talking about an ASL rotator to point it in the right direction. If you're dealing with something that's relatively omnidirectional, you don't get the gain, but you don't have to deal with the rotator. Especially for the linear satellites, some of them being very weak, it's probably a time to upgrade and have the gain. As you're building the station, though, and as I did, you'll come to the realization that building a great satellite station is building a really bad EME station for 2 meters and 70 centimeters. And I'm fine with operating really bad stations. That doesn't bother me at all. I love to come to field day and PAARA in the park and things, and y'all have 500 watts and amazing antennas and whatnot. But I'm in a park with a 5-watt transmitter I built out of junk, and I threw a wire in a tree. So the other end of my QSO is often doing all of the work to make this possible. I'm often making contacts with folks with amazing antennas. And this is another case where you can do that. There are documented moon bounce contacts off of J-poles. Now, the other guy had a 700 element antenna or something, but you can say that you did this with a J-pole or a dipole or something. And so as you build this great satellite station for 2 meters and 70 centimeters, you've built a pretty bad EME station. But with the larger stations, especially digital modes, it's completely workable. You probably want some more power. I've never heard of an EME contact on less than 100 watts, although somebody's done it. 500 is a bit more common. I'd say probably start there. So let's talk about what moon bounce contacts take. Ignore the graph for a moment, and let's think about the relationship between the Earth and the moon. At any given time, the moon can see half of the Earth. And over the course of a year, the moon can see every single point. We have seasonality, right? When it's summer here, we're pointed towards the sun, we're also pointed towards the moon. Over the course of a year, if you're trying to bounce a signal from the Bay Area, we're about 122 degrees of longitude. Over the year, you can see every other point as a reflection off of the moon. It means you can make a contact with it. When the moon is rising from our perspective at around, it's rounded, call it 120 degrees longitude, it's setting at 60 degrees east, which is a line that goes through the middle of Russia, through Kazakhstan and eastern Iran. And every point that is, from our perspective, east up to that line is reachable by reflecting off the moon. So the entirety of North America, except for Alaska, all the way through Europe, the entire Middle East, the entirety of Africa, Madagascar, basically go all the way up to this line in eastern Iran that's just shy of India, basically. And then as the moon continues rising in our sky, it's setting all those folks, so you lose them, and you lose Madagascar, and you start losing Africa, and you lose Europe. But it's rising over the Pacific Islands. It's rising over Oceania. It's rising in Australia. It's rising in Southeast Asia. It's rising over China. You eventually get all the way back to that line. You've got the entire other side of the globe. So some of these points, you're only going to have minutes to make a contact. Good luck. I recommend scheduling that. But it's theoretically possible. And in the summer, in the Northern Hemisphere, we're going to be tilted towards the moon a little bit. And it's going to move that line a little bit and give us complete polar coverage. And then in the winter, it's going to shrink that a little bit for us, but it's going to tilt the South Pole towards us. You make a contact with the station in Antarctica, theoretically, if any of them bothered to build a decent antenna. I don't think they have, but if you know anyone that's a researcher and heading to Antarctica anytime soon, they can borrow some of my gear. Chart here, it's a lot to digest, but what I want you to take from it, we have frequency on the x-axis here, and on the y-axis we have noise. So for a moon bounce station, you really have to care about signal to noise ratio. You've got 250 decibels of loss, 260, 270, depending on a bunch of conditions, between you and the other station elsewhere on Earth trying to make that contact. And meanwhile, you've got noise from the sun. Turns out it's really loud. You've got noise reflected and generated by the Earth itself. You've got galactic background radiation. And this isn't flat with frequency. So 2 meters is right about here. It's still kind of noisy, but it's coming down. And 70 centimeters is over here. Not quite at the minimum, but pretty close to it. So 2 meters is really popular for moon bounce. There's lots of stations, but it's a little bit harder due to the noise floor. 70 centimeter is close to ideal in terms of noise, and there's still lots of folks to contact. It's kind of a sweet spot for noise and complexity of your equipment. It's still a frequency range where you can hand cut a Yagi and build your own antennas and that sort of thing relatively easily. You also find a lot of activity actually sort of right at this sweet spot of noise. That's around 1.2 gig. We have privileges in that frequency range too. And at that range, you could still cut a Yagi. You'd need better workmanship and tools than I have. Dishes and horn antennas and things like that get to be more feasible at that range. And you'll see, what was that? And you can always wave the magic wand of the credit card and pay somebody else to make it. That is an excellent point. My magic wand doesn't sparkle as much as I would hope. I want to address something. As I say, building a great satellite station is building a bad moon bounce station. And I tell you to work with circularly polarized antennas. One of the first bits of advice that you'll find if you Google that is not to use a circularly polarized antenna for moon bounce. I'm going to respectfully disagree and say that circular polarization is great for moon bounce, especially for beginners. The other station is doing more of the work than you are. You are not at parity. You are not capable of making a contact with an equivalent station to yourself. You are depending on them being better than you. And circular polarization always has the same match to any linear. You're always down 3 dB. And we're down 250 bouncing off the moon. What's another 3? You have so much complexity around polarization on this path that taking that out of the equation, you're basically assuming that the other person isn't also using a circularly polarized antenna. That's the only downside is if they're also using a circularly polarized antenna and they are set up in the same handedness, right? Their right hand and your right hand. When the signal bounces off the moon, that handedness reverses. Any right hand signal becomes left hand. You now have a negative 30 dB loss. I promise you, you will not be able to hear them. I don't care how big your antenna is. You will not survive an additional negative 30 dB on a moon bounce path. But for literally any other antenna, fine. You don't have to worry about the polarization when you're building a bad EME station. And just 2 examples of polarization matches that you'll have to worry about when you want to build a good EME station. First is geometry. So let's assume that I'm trying to make a contact with someone in Europe. I'll answer that question in a minute, Andy. If I'm trying to make a contact with somebody in Europe, I've got about a 90-degree angle of that reflection off of the moon. So if I'm vertically polarized, they're going to receive it rotated 90 degrees. It's horizontal polarization. So unless I'm making a contact with my neighbor, there's always some rotation due to that reflection angle off the moon, due to the geometry between our 2 locations. More importantly, there's also an unknown and changing rotation caused by the signal going out through the ionosphere and then back through it again after reflecting off the moon. It's called Faraday rotation. This is unknown and changing on the order of minutes. So you'll have a couple of minutes of a great match and then they're gone. And that's just normal for moon bounce. And the interesting complication here is when HF is doing well, when we have high solar activity and great refraction through the ionosphere, moon bounce is harder because Faraday rotation is changing faster due to those ionospheric disturbances. A question from Andy?
Yeah, I think maybe around 20 years ago or so, there was a PAARA meeting with a speaker who used a TVRO satellite dish of some kind. And on 1.2 gigahertz, he was making contacts to Europe with, he had a vacuum tube that he water cooled it to transmit. Brilliant topic. By the way, you can find this in Paragraph's archives. Just look for satellite, the keyword satellite TVRO. It's somewhere in the archives. I don't remember how many years back.
And so as you get to a gigahertz or so, the first band that we have privileges in above a gigahertz is 1.2, if I remember correctly. Dishes and horn antennas start to be really viable, and parabolic dishes are great for narrowing that beam width. But an advantage is you have several different types of horn antennas that are circularly polarized, and simply switching the polarity of the input or having a common and switching between two sides of the horn switches the handedness of the circular polarization from right to left. And so there's a convention in moon bounce, as everyone tells you not to build circularly polarized antennas. As soon as you hit 1.2 gig, they tell you only build circularly polarized antennas. And there's a convention that you transmit on right hand and you receive on left hand. You've just got a TR switch at the horn, which you've probably got already because you've got at least a low noise amplifier, potentially your entire main power amplifier at the horn. You're just toggling between two polarities. So I carry that down into 2 meter and 70 centimeter, where we're building satellite stations. Why not build circularly polarized here and skip the polarization problem for a little while longer? And when we want to build our Earth Moon Earth mega station, we're going to build a big darn dish anyway and still be circularly polarized, and we'll have some experience and know how not to screw that up. From there, speaking of screw ups, let's talk about the field day station. And I am making light and using self-deprecating humor. That is not serious. This was designed to be a great satellite station and a really bad moon bounce station. I had high hopes to make one digital moon bounce contact. Instead, I made one satellite contact. Started with dual circularly polarized high gain Yagi Udas. We had 6 elements on each on the 2 meter, so 12 elements total. I believe it was 18 elements total on the 70 centimeter side. That was perched on top of a completely home-built Azel rotator. I did not design this from scratch, although I very loosely followed the designs that I had found. The only part that I didn't build was an IC 9700 transmitter or transceiver. Love that radio. 2 meter, 70 centimeter, and when you want to deal with moon bounce, 1.2 gig. Command and control between the station and the rotator was a shielded CAN bus over Cat6. And this I'm actually rather proud of. I was kind of nervous how that would work on field day, but that allowed us to have 50 feet and probably could have gone to several hundred of cable between the operating station and the rotator without having to worry about interference from HF. Turns out the automotive folks are really, really good at designing things that don't care if they're sit next to a transmitter. On the software side, gpredict was running the show, and I haven't mentioned this or recommended it, but when you get beyond wanting to figure out where satellite is off an app on your phone, there's lots of larger software packages, and most of them include extra features, controlling the rotator, tuning the radios, handling Doppler shift. gpredict is one of them. It works well. There are some asterisks behind that statement, but it is something I do recommend. And because Field Day is a spectator event, I tried to put the satellite map up on a 40-inch TV for everyone to see. Let's talk about what went wrong with that. That's point number 1. So you might notice in the picture that the TV is off. It's not really how I hoped. And what happened was we had a battery-powered radio and an inverter off the battery-powered TV, because TVs are AC input now for some reason, connected to a laptop. And this formed a ground loop between the HDMI and USB connections. And I will say that Lenovo seems to have done a very good job of designing protection circuits for that event, because none of the blue smoke left any of the devices. However, half a second or so after plugging in the TV, the picture would start coming in and out as that protection circuit turned it off. And so no TV, that's fine. We'll operate off a monitor. Second one, we didn't notice until evening Saturday, maybe early morning on Sunday. all your prediction tools, they're forecasting where a satellite's going to be, starting with something called TLE data, or Keplerian elements. This is a measurement of where a satellite is and how fast it's moving, what direction it's moving in, made by someone with better equipment who knows what they're doing, hopefully. Usually space agencies, governments, militaries. Department of Defense tracks just about every object in space, and they publish most of it. So that TLE data is the input to algorithms that fast forward in time and predict where the satellite's going to be. And that's how all your past predictions are produced, regardless of what software you're using. But the TLE data itself is not perfect. It's often missing critical information like drag coefficients. It's rounding to a few decimal points. And the algorithms that your software is using are not as accurate as they could be. They're trying to produce a good enough result quickly. They're not running full supercomputer simulations of drag in the upper atmosphere. So the older this TLE data is, the less accurate your past predictions are. So all these software tools have some provision to update it. You should turn that on. Most of them have it on by default, and you should turn it on. And I did. I made sure that the day before on field day setup, before I left the house, the GPredict's TLE data was up to date. Somehow GPredict was still using the old data. And since I'd set up a brand new installation for field day, it wasn't running anything else. This wasn't my personal install, my work machine. The data that I was overwriting was the original that shipped with GPredict when it was built, 6 months ago. And so somehow, even with up-to-date data, it did not refresh its predictions, and the passes were off by massive amounts. The satellite positions were off by 20 degrees. We had passes that GPredict predicted would occur that every other tool showed that the satellite never came above the horizon, and vice versa, where we missed passes that came above the horizon, but GPredict said they wouldn't, so it didn't show it to us. To this day, I don't know why that happened. But when you're setting up your station, and maybe periodically when you've been operating the same software for a little while, go check the predictions against anything else and see if they make sense. Because as soon as I had Soren next to me pulling passes on his phone, none of the data made sense. 2 pieces of software might produce a degree or 2 of difference in position of a satellite. That doesn't matter. Might produce 15 seconds difference in key events like acquisition and loss of signal times. If you see anything more than that, if you see errors in minutes, disagreements in degrees, tens of degrees, there's something very wrong. More impactful bit was the 70-centimeter antenna. So I talked about how these antennas were 2 Yagis that were tied together at a Y. And so you have 2 50-ohm tuned 70-centimeter Yagis that are tied together at a Y that's doing an impedance match and taking that down to a single bit of coax. And this antenna kept shorting, and we kept pulling it down and analyzing it and figuring out what was wrong with it. And the short would go away, and we'd say, okay, well, if you hold the element just like this, we duct tape something in place and we put it back on the rotator. And then a couple hours later, the SWR is 40, and well, I guess it shorted again. And eventually, this got torn apart, and we found that at the Y, the output side coax would rotate slightly, and a bit of the shield would rotate into contact with a solder joint that was the center pin and short out at the Y. So we rebuilt the antenna on the back of a U-Haul with Clark's portable electronics kit and Shree's experience with building EME antennas and my frustration and profanity, and we built we built an antenna. What was that? We also had some coupling between the antennas that was feeding back into the other side of the radio, overwhelming the filters there. So we were swamping ourselves out on transmit. That's not super important, but it means that we can't verify correct tuning and reaching the satellite with duplex. And then the Azel rotator, which worked very well and pointed the antennas very accurately, was producing so much noise that we basically couldn't hear any satellite flying. And turns out that wasn't a single cause. There's half a dozen different causes for that. Let's talk about what went well. First of all, we made the contact. On field day, you get 100 bonus points for making a single satellite contact, and then every other contact is just regular points. We made the one, we got the 100 points. Process did indeed fail successfully. The CAN bus command and control system that I was honestly more worried about than any other part of this system had no problems. It worked flawlessly. We had no communication issues with the rotator. Power was running over the unused pairs on that line. Worked totally fine. We rebuilt the 70-centimeter antenna on the back of a U-Haul with tape. There's about 30 zip ties there, and put it back together, and it did end up in service, and it did work. Had an SWR of 3.5, but that's better than 40. We found and corrected, worked around everything that got thrown at us through my hubris and design choices. We have a community here that saw this as a fun challenge and nothing else. If anything, this community was trying to remind me the entire time that this is fun, even if it's not working. And normally I'm the one saying that. So I really appreciate the way the community came together. And I really appreciate how everyone is actually providing that moral support, but also actually providing practical support. You get any 20 of us or so together, and you could probably rebuild society with the junk we keep in our cars. We had electronics kits and zip ties and soldering irons, and we had Ben and Chuck chasing cables for me when I thought the USB cable was the cause of the display problems. And just to be in a park, effectively, I mean, yeah, we could have driven to a store or something, but just to be here with just the stuff that everyone carries and be able to rebuild an antenna on the back of a U-Haul and bring it to operational standards is great. It's one of the joys of the ham radio community to me to see that. And some of the problems we couldn't work around, or I mean, we couldn't correct, but we could work around. The rotator, I couldn't get that thing to shut up and let us hear a satellite. So we pointed the antenna at where the satellite is going to be and turned it off. We just waited for the satellite to meander across the path of our antenna. But with a 20-degree beam width, I've got a third of that satellite's pass where I've still got enough gain to hear it. It actually surprised me how little rotation you need, even on really weak satellites. You can just point it and leave it alone and let the satellite come to you and still have several minutes of usable operating time. But the most important bit of this to me is all of this can be better next year because of what we learned. Multiple antennas and switching one to the next. Yeah, that's a completely valid strategy of just switching your antennas. And this is why my direction has shifted a little bit from these absurdly high gain, over-engineered antennas that I designed to just, what if I just put up an egg beater? I don't have to point it. I have to put it away from things and make sure the upside is up. Right? The disadvantage there and on egg beaters, and I encourage you to go down the research rabbit holes. They're not quite as good at receiving the satellite just as it comes up over the horizon. You've got a longer distance. You've got noise from the ground. It's a little bit harder to do. So the high gain directional antennas really give you those few extra degrees towards the horizon. If you're trying to make the longest possible contact, that's what you want. Folks, that's what I have for you tonight. I believe Bob described that as the most effort for a single contact on field day.
Test. Indeed.
All right, everybody, who's any questions in the room? Oh, whoa, we'll go this way and go that way. Here you go, Soren.
Thanks, Justin, for walking us through all these challenges and successes. My question was, when you did all this research, did you figure out, or is it ever listed anywhere, what was the first Earth, Moon, Earth contact? And if it has anything to do with the Stanford dish research thing, because like the first amateur radio contact through the moon. Thank you.
There are definitely records of it. I do not remember the details. I don't believe it was Stanford, but yes, there's a fairly well documented historical record on this, because it was not until relatively recently in radio history that we had enough low noise gain to actually make that possible. First ones were, of course, CW. Now you can do it with less power and a little easier with digital modes. But yeah, it's documented. I don't remember what it is though.
And Mark.
Two questions. First, you mentioned asterisks on recommending forget the software, G Finder. And so what were those? The second question is, you said that your cross coupling caused you to lose full duplex. If it's crossband, it seems like there should be a ton of attenuation in the crossbands. Wondering how that happens.
So I do recommend gpredict. I do think it's a great software suite. It runs on all platforms. It controls basically any radio or attenuator or any radio and rotator that you can throw at it. My asterisk behind it is around that TLE data. I don't know why. I updated the TLE data using the software itself. I confirmed that it is updated. I confirmed that it's from a good source, and it gave me predictions based on the old data. And I don't know why. I know how to identify that when it happens in the future, but I don't know how to prevent it. And so that's my big asterisk. I apologize. Refresh me on the second question. Oh, the full duplex loss. Yeah. I believe there was just enough common mode current coming in the other way to swamp out the SDR on the other band. I don't know exactly what was happening, but when I reproduce this in my backyard with a boatload of common mode filtering on the coax, it goes away.
Okay. We'll go here counterclockwise. I'll get right with you. Here you go, Andy.
Well, Murphy hit you in so many ways. So next year, maybe it would be safer to have one ham on the team turn the antenna manually.
Yeah, it is. So I did over-engineer the station, and a lot of that over-engineering is what bit me. A simpler station would have had less possible things to go wrong. Like you said, this is more for the education and the fun, and I like overkill. For your own satellite stations and practicality, especially first contacts, yeah, don't worry about a rotator, especially at first. Either use an omnidirectional antenna or go point the antenna and walk away. You don't have to point it precisely and move it in tenth of a degree increments. None of that matters.
Hi, W6EFI.
You've met.
Yeah. uh, uh, Back to the ISS. Really easy thing to do with the ISS is to grab their SSTV, their SSTV events. Man, they could just come blasting in with pictures, and all you need is sit in your car with the vertical on the roof of your car and just record it, and it's just beautiful stuff. So that was my first experience with satellites. Very rewarding. The question is, I have a question, which is why CAN bus?
Yeah. So pretty much all of the open source or homebrew designs for rotators are using a serial bus, RS-232. Almost all of them are just using USB. And getting USB to go 10 feet under good conditions is practically impossible. You can get 30 on USB 1 under decent conditions, but put that next to your HF transceiver and key up and see what happens. So that's how my first projects were. You know, it's an Arduino or a Raspberry Pi Pico in this case running the show. So you've got that USB serial connection as it's a a cheap, easy way to communicate with it. CAN bus popped into my head because I'm looking at this and I'm thinking it's automotive, it's differential signaling, it's already fairly robust for distances and interference. And I look around the shop and I see, okay, I've got a roll of shielded Cat6. So that's twisted pair, got a good shield on it. That's ideal for something like CAN bus. And more importantly, in the junk drawer, I have I squared C to CAN bus modules that I already have. And I have no idea what project I bought them for, to be honest. And I'm like, okay, I wonder if this would work. And when I start poking at it, before I actually build it, I don't see a lot of reasons it couldn't, and I don't see a lot of other great options. I mean, you can make RS-232 run over shielded cable for reasonable distances, but do you have a serial cable anywhere? My computers don't have that anymore. So I said, you know what, let's try it. And I don't have a great HF station at home. And so I went over to a friend that had a 500-watt amplifier, and they had a dipole that was low enough that I could reach it holding my hands above my head with a ladder. And so I set up two devices at either end of a 50-foot bundle of Cat6, basically just sending data over CAN bus back and forth and logging it. So I could see if there were any errors, right? So I take this 50-foot coil of Cat6 that's got this data going back and forth. I just hold it up to 500 watts teed up on the dipole here, and I'm thinking this is worse than anything will happen on field day. And I wave it around a little bit, and then I go check the logs, and there's no data loss. I said, okay, well, that'll work. It worked, and I had it. Sure.
I was just going to say the same thing.
I mean, I don't know why anyone wants that, but okay.
Excuse me. Okay, I think we had another question here.
Yeah, I just wanted to make a comment. Let's see, one of the early moon bounce people that participated in that was Robert Sutherland. He was W6PO, and his daughter. I met her back in the 1990s, and she was active in the 1010 clubs back then.
Yeah, I read a lot of the history of it, but I had a really technical bent reading it. So if you go down the technical rabbit hole, Princeton has an amazing EME station as well. But there's a lot of history and a lot of it is still accessible in public, unlike the early days of radio itself.
All right. And speaking of Zoom, if anybody does have questions, put it on chat and we'll get you. Here's Daryl.
Yeah, I went to a presentation. It was at the DX Club. I think this was back in 2009 or 2010. Anyway, there was a presentation on the guys that did the moon bounce EME with the Stanford dish. That was pretty impressive. But when they did it, it was only like, I hate to say it, but it was like an exclusive group of people that could be there. And there were some, I guess, dignitaries there as well. The interesting thing, I didn't realize it, but the Stanford dish is actually rotated on a railroad track. So when they rotate it, it's actually motion around on the actual railroad track mechanism. But they were able to do it. I think they did it on 1.2 gig. I think they did it on 1.2 gigahertz, and they actually did have some recordings of it, and the delay was pretty impressive between when you transmit it and the other person heard it. It's like a second or two at least. I mean, because remember, you're talking about close to 500,000 miles round trip. So, and the latency has got to be up there. So anyway, I had gone to that presentation. It's been a long time since I saw it, but I did see that presentation.
Anybody else in the room?
One up here.
Oh, coming up front.
Yeah. You said you did receiver work in some kinds. Do you have a noise figure meter?
I have a noise figure meter. Nope.
You know what one is?
Yep.
Okay.
Zoom control. Anybody on chat? So it's been many, many years since I was working the birds. I'd be at home. I'd predict this, the passes. I had my radio all set up with the Dopplers, and I would use the arrow antenna. And I had fun. But as you were talking about, it can be simple. And so I would sometimes get off work and I would see a prediction. So I'd pull over to a park or something. I'd take my HT, I'd put a metal telescoping antenna, turn the HT upside down. I'm guessing that's for better takeoff angle. And I call, and I've made several contacts on an HT to a satellite that way. So
it can be that simple. And something I didn't go over today that Connie, you made me think about is you have slow scan TV, which is one-way communication, but it's interesting for special events from the ISS. You've got lots of things in orbit that are transmitting unencrypted data, right? All of NOAA's satellites, essentially some unencrypted local TV and lots of stuff up there if you know where to point. So all of that's available to you, depending on what you can build. And there are two-way digital satellites as well. There's nothing really interesting in orbit right now. You've got some APRS digipeaters, not really making a QSO over those. But there are things in the launch plans and things in orbit provisioning right now. If you watch AMSAT, that some of that will be available to us again, and it has been in the past. It's just everything that was doing store and forward messages or whatnot ceased to function or ceased to be in orbit.
Soren, it might get really popular. We may need a satellite tab in the Discord. Oh, EME. All right. Got Elliot here.
The Discord channels now are longer than a single page on my phone can display, though. So I have a complaint to file with our server admin. It's 250 dB loss to the moon. I don't think you'd survive a boost to Mars without some novel silicon chemistry or some novel transistor chemistry.
So you talked a little bit about doing FM over satellite repeaters. So sort of two related questions. One is there enough bandwidth available to do anything other than CW or digital over moon bounce? And if not, is it a limitation of the link budget, or is it like an actual, or is it more of like a legal issue?
So over moon bounce, you don't have legal issues. You don't have bandwidth issues. Over the satellites, over the linear transponders, you're dealing with power budget and bandwidth, which is why you're on SSB and CW. You're not even doing constant power things like FT8. Not that it can't, but you have been asked not to by the people operating them. And the amateur satellite community would come and hurt you if you didn't follow their recommendations. For moon bounce, the issue is noise floor. So the wider your received bandwidth, the higher the noise from all of the sources. And so getting a high enough SNR to be decodable, even with the best digital methods that we have, it's really hard to get wider than CW. Actually, CW is kind of the hard one on moon bounce compared to the digitals these days. You're not getting an SSB contact outside of the multiple kilowatts of amazing antennas. Yes, with kilowatts and amazing antennas. Yeah, yeah, yeah. So that's just thermal noise.
So Justin, you mentioned there's nothing interesting on the ham radio side in the orbit right now, and
for digital satellites, for digital stuff, yeah.
And that's true statement for our location. If you are not in North America and you are in the more like Eastern Hemisphere, there is the most awesome QO100 satellite
in geosynchronous orbit. It's always there. It's amazing bandwidth.
It's in
all
the
kinds
same
of
location.
Running.
So people work that what looked like a small TV satellite. And it truly it is, because the downlink is 10 gigahertz anyway. So you just use commercial LNA on the satellite. So you get the downlink super easy. But we need one of those over the Western Hemisphere, because through that satellite, there's tons of power. It's at a fixed location all the time. and there's a lot of bandwidth. So people do sideband, just rack chewing on it, digital ATV, CW, FT8, whatever you want. They don't. I don't think they do FM, but
Well, and there's just a huge a cone that can see it too. Like we can't see it, but the area that it can be seen is massive.
essentially half the Earth.
Yeah.
So again, it's like from India to little bit of Brazil.
Yep.
That's the footprint it covers, and it's incredible. We need one of those here in the world.
So
Did you?
It's geosynchronous, which is halfway to the most.
Anyone have like Elon Musk rich friends, and let's get a sponsor for one of those.
So before I grab the next question, just something to be aware of when we talk about amateur satellites or amateur radio on a satellite. With the exception of that satellite, everything we have in orbit is either defunct something else that was reconfigured for amateur radio, because when you launch satellites, you tend to make them very configurable for future use, or is a stowaway, right? You have amateur radio gear that got taped to the side of something that was going to launch anyway. And so you have virtually no power, weight, or volume budget, but somebody was nice enough to let you hitch a ride. Or you have things that were built with amateur radio as one of the major goals, often by a university group, that is a CubeSat or a micro CubeSat. These tiny little things that weigh nothing, have no power budget. They're often letting a wire out as their antenna. And those two are effectively stowaways, because how most of those CubeSats are launched is we need a small amount of ballast for this thing we're going to launch to even out weight distribution. And rather than put a lead brick here, we will take your CubeSat and we will drop it off on the way. There were at one point CubeSats in orbit, I don't know if they're still in orbit, that were sent up to the ISS on a resupply mission, and they were placed in orbit on a spacewalk. The astronaut threw them into orbit because they were already there.
Here you go.
So I noticed you omitted probably one of the most powerful satellite relays that is unencrypted, unauthenticated, but highly illegal, and yet used throughout, let's say, South America, the Navy fleet comsats, where between 250 roughly and 265 megahertz, not that I may have ever done this, truckers, loggers, and everyone else, it seems, who's running a small business in South America is using US Navy satellites to communicate over vast distances in the Southern Hemisphere.
I will say two things on that. Number one, if you don't want someone to use your thing unauthorized, then you should design better security.
Amen.
Number two, if you don't want to get caught doing something illegal, you shouldn't talk about it.
I just highlighted that it's, of all the many things you've talked about tonight, it is probably one of the most infamous satellite relays.
There's a reason the First Amendment comes before the rest of them.
Followed by the second.
Yes. The right to free speech includes the right to shut up.
So you don't know a hack for Starlink downloads yet?
No comment.
Anybody else? Questions in the room or on Zoom? Okay, I think we got to wind it up.
I think we gotta, yeah, I think we
Bob
gotta
looking
wind it
at
up to
me.
get ourselves.
Hey, Justin, thank you very much.
All right.
So just want to let anybody know, if you found Justin's technical attributes very interesting and informative, he is our Wednesday net control in the 9 a.m. TalkNet. Keep him busy. Thank you so much.